Something has changed. In the last few years, the solar system has begun to feel different. Not in any dramatic Hollywood sense, just different. Objects are arriving that shouldn't be here. Their chemistry doesn't match anything we've catalogued. Their trajectories suggest origins we can barely trace, and the more data we collect, the more unsettling the pattern becomes. This is not about speculation or conspiracy theories. This is about documented observations, published research, and questions that scientists are now asking out loud, questions they never thought they'd have to ask. Let me tell you what's happening right now, because what we're witnessing might be the beginning of something we've never experienced before. On a clear night in 2024, astronomers detected an object entering our solar system from interstellar space. They catalogued it as Atlas, the third confirmed interstellar visitor in human history. The first was Oumuamua in 2017, elongated, accelerating strangely, gone before we could study it properly. The second was Borisov in 2019, a comet, relatively normal, but from another star system. And now this, Atlas. But this one is different. This one contradicts everything. When astronomers analysed the spectroscopic data, they found something immediately wrong. The composition of Atlas is backwards, completely backwards from what comets in our solar system look like. Our comets are water ice with some carbon dioxide mixed in. Water dominates, CO2 is secondary. That's the standard ratio. That's what 4 billion years of solar system chemistry looks like. Atlas is the opposite. Carbon dioxide ice dominates the structure. Water is secondary. The ratio is inverted. Think about what that means. This object didn't form anywhere near a warm star. It formed in the frozen outer regions of some distant planetary system, far beyond the habitable zone, far beyond where water ice could be the primary volatile. It formed in a place where temperatures were so low that CO2 froze solid before water ever had a chance to dominate. This is the chemical signature of a world we've never visited, a planetary system with different conditions, different distances, different formation processes, and now it's here, drifting through our neighborhood. But there's more, something that makes Atlas even stranger. After Atlas was ejected from its home system, it spent billions of years wandering through interstellar space, billions of years in the void between stars, completely exposed to galactic cosmic rays. These aren't the kind of radiation you experience on Earth. These are high-energy particles accelerated by supernova shockwaves, by magnetic fields around neutron stars, by processes so violent they defy easy description. And out there in the darkness, there's no protection, no magnetosphere, no atmosphere, nothing, just raw exposure. Cosmic rays slammed into Atlas continuously for eons. They broke apart organic molecules on the surface. They shattered chemical bonds and reformed them in new configurations. They created complex carbon chains that don't form naturally under normal conditions. And slowly, over incomprehensible stretches of time, they built something, a crust. Research teams analysing the comet's surface properties estimate this radiation-processed layer extends approximately 5 meters deep into the nucleus. 5 meters of material that has been fundamentally transformed by exposure to the galaxy's most intense radiation environment. The color is reddish, the structure is dense. This isn't the pristine ice from the comet's birth system anymore. This is something else, a natural armor plate forged by time and space. And for billions of years, nothing disturbed it. The comet drifted in silence, its secrets locked beneath that ancient crust, until it entered our solar system, until it got close to the sun. As Atlas approached the inner solar system, sunlight began to heat its surface. For the first time in billions of years, energy penetrated that radiation-hardened crust, and something cracked. The frozen volatiles beneath the surface, compressed and sealed for so long, suddenly had an escape route. Carbon dioxide gas began to sublimate, forcing its way through fractures in the crust. Pressure built, then released. A coma formed around the nucleus, dense, pulsing, expanding outward into space. It looked like the comet was breathing, like an object sealed for ages had suddenly come alive. Astronomers watched this happen in real time. The brightness increased, the spectral signatures changed. Hydroxyl radicals appeared in the data, indicating water vapor was now escaping alongside the CO2. The comet was venting its interior into space. The sun had illuminated something that had been dark for longer than our entire solar system has existed. But here's where the story takes an unexpected turn, because while scientists were studying Atlas, they realized something: we might get more than just remote observations. We might get physical samples. There's a spacecraft near Jupiter right now, not designed to study comets, not equipped with any special instruments for interstellar research, just a probe on a routine mission, equipped with a mass spectrometer for analyzing local gas and dust. And according to trajectory calculations, there's a chance, a real possibility, that this spacecraft will pass through the tail of Atlas. If that happens, if the crossing occurs, the mass spectrometer will analyze particles from the comet's tail. It will read the molecular composition atom by atom, isotope by isotope. It will capture the chemical fingerprint of material from another star system. We wouldn't have to launch a special mission. We wouldn't have to wait decades for an intercept trajectory. We'd just get the data accidentally, because two objects happened to be in the same place at the same time. The scientific community is quietly hoping this crossing happens, because if it does, it would be the first time humanity has ever analyzed physical material from another planetary system without leaving our own. The first real sample from beyond, not meteorites that crash to Earth, not spectroscopic inference, actual particles captured in situ. That's the opportunity here, and it's entirely dependent on orbital mechanics and timing. We'll know soon enough. But Atlas isn't the only interstellar visitor making scientists rethink what's arriving at Earth. Military satellites detect objects entering Earth's atmosphere constantly. Most are natural meteors, some are space junk. Occasionally, something registers that doesn't fit either category. A few years ago, sensors recorded a high-velocity impact over the Pacific Ocean. The object hit the atmosphere at incredible speed, far faster than anything in a stable solar system orbit should be moving. It disintegrated instantly, fragmenting into microscopic particles that scattered across the upper atmosphere. Then it was gone, just another flash in the data logs. Except someone looked at the velocity more carefully, and they realized something. The speed was above solar system escape velocity, which meant this object couldn't have originated from anywhere in our neighborhood. It had to come from interstellar space. An interstellar meteor, the first one ever confirmed. A team decided to search for the fragments. They organized an expedition to the impact zone, dragging magnets across the ocean floor, filtering sediment, looking for anything unusual. And they found something. Microscopic metallic spheres. Tiny, perfectly round droplets of metal that formed when the meteor vaporized in the atmosphere and then recondensed. The composition didn't match Earth. It didn't match typical meteorite alloys. The ratios of elements were wrong. The isotopic signatures were off. This was material from somewhere else. The spheres are still being analyzed, but the implications are already clear. Interstellar objects don't just pass through the solar system, they hit Earth. They've been hitting Earth for millions of years, and we never knew. Because how would we? How do you distinguish an interstellar rock from a local asteroid if they both end up as fragments in a museum drawer? Researchers at several institutions have been working on a massive computational model. They're simulating the trajectories of 100 billion hypothetical interstellar objects around the solar system. 100 billion. Not because they think there are that many, but because you need a statistically significant sample size to understand where the real impacts should be coming from. The simulation tracks objects entering from all directions, influenced by the sun's gravity, by the orbital motion of the planets, by the solar system's movement through the galaxy. It calculates impact probabilities for Earth based on time of year, latitude, and direction of approach. And the results look like a battlefield map. There's a primary stream. It arrives from the direction of the sun's motion through the galaxy, the apex in the constellation Hercules. This is the head-on collision zone. Objects drifting through interstellar space that happen to be in the path of our solar system's galactic orbit get swept up like insects on a windshield. The model shows that during winter months in the northern hemisphere, Earth moves directly against this flow. Impact probability peaks. The northern latitudes, especially near the equator, get hit most often. We're not just sitting in empty space. We're traveling through a galactic swarm, a constant rain of interstellar debris too small to see, too fast to track, hitting the atmosphere and burning up before anyone notices. But some of them survive, some hit the ground, and right now they're sitting in collections labeled as ordinary meteorites because no one thought to check for interstellar origins. That's about to change. The next step is to re-examine meteorite samples from institutions around the world. The researchers are looking for isotope ratios that don't match solar system formation models. Oxygen isotopes in particular are the key marker. Every planetary system has a slightly different isotopic fingerprint based on the molecular cloud it formed from. If you find a rock with the wrong oxygen isotopes, you've found a visitor. And the simulations suggest there should be hundreds, possibly thousands of interstellar meteorites already in our collections. We just didn't know what we were looking at. Not every interstellar candidate is sitting quietly in a laboratory. Some are still being investigated. In early 2025, a fireball streaked across the Russian sky. Initial reports assumed it was space junk, a defunct satellite maybe, a booster stage from an old rocket. The trajectory was too shallow, too horizontal. It looked artificial. But when researchers reconstructed the event, they recalculated the velocity. 30 kilometers per second. That's impossible for man-made objects. Satellites and space junk re-enter at 7 or 8 kilometers per second, maybe 10 if the orbit was highly eccentric. 30 is something else entirely. This was a natural object, fast-moving, small, probably around 1 meter across, and it survived long enough to drop fragments. Teams recovered pieces from the impact zone, stony chondrites, typical-looking meteorite material, but the labs are running isotope analysis now, checking for anomalies, comparing the ratios to known solar system values. If the numbers come back wrong, if the oxygen isotopes don't fit, then that fireball was interstellar, another visitor that made it all the way to the ground. The results aren't public yet, but the fact that researchers are even checking tells you how seriously this is being taken now. Because the question isn't whether interstellar objects hit Earth, the question is how often. While some scientists are tracking objects entering the solar system, others are looking for something even older, something that has been hiding in plain sight for 13 billion years. The first stars. When the universe was young, just a few 100 million years old, the only elements that existed were hydrogen and helium. The first generation of stars formed from this primordial gas. No carbon, no oxygen, no metals. Just the simplest atoms collapsing under gravity and igniting fusion. These stars were massive. They lived fast and died young, exploding as supernovae and seeding the universe with heavier elements. But not all of them were massive. Some were small enough to still be alive today, burning quietly, unchanged for billions of years. The problem is finding them. Low-mass first-generation stars would look almost identical to normal stars unless you examined their spectra very carefully. And even if you did, there's a complication. Stars don't exist in isolation. They orbit through galaxies, passing through gas clouds, accreting material over billions of years. They get contaminated. Their surfaces accumulate heavy elements that weren't part of their original composition. They wear chemical masks now. So when you observe a star with extremely low metal content, you can't be sure if it's truly primordial or just very old and very clean. The distinction matters, because a real first-generation star isn't just ancient, it's a relic from a universe that no longer exists, a universe before planets, before complex chemistry, before anything familiar. Astronomers have been searching for decades, and recently they found something. In a nearby stellar system, researchers detected a star with a metallicity 100,000 times lower than the Sun, 100,000 times less contamination. This is the purest star ever observed. The chemical analysis shows almost no heavy elements, just hydrogen, helium, and trace amounts of lithium. The signature is unmistakable. But even this star might not be truly first generation. It could be second or third, formed from gas that had been only lightly enriched by the earliest supernovae. The metallicity is so low that it's hard to say for certain. What astronomers really want is to find a cluster of these stars, a group that formed together, all with the same primordial composition. That would be definitive proof. And then, using gravitational lensing, they found one. A massive galaxy cluster bent the light from an extremely distant region, magnifying the view just enough to resolve individual stars. And in that magnified field, astronomers detected a group of stars with spectra unlike anything in the modern universe. No metals, no carbon lines, no oxygen absorption, just hydrogen and helium. These are stars from the first generation, stars that ignited when the universe was an infant, stars born before galaxies had fully formed, before the cosmic web took shape, before the heavy elements that make up planets and life had been synthesized. A glimpse into the universe as it was, before everything we know began. The discovery was published quietly. No press releases, no headlines, just a paper in an astronomy journal, presenting the data and the implications. But the significance is staggering. We're looking at light from objects that have been burning since the beginning of time, and they're still there, still shining, waiting for us to notice them. While astronomers search for ancient stars, planetary scientists are discovering something equally strange. Some of the hottest, most inhospitable planets in the galaxy are producing water. Not on their surfaces, deep inside. These are planets that orbit so close to their stars that surface temperatures exceed 1,000 degrees Celsius. Any water on the surface would evaporate instantly, stripped away by stellar radiation and extreme heat. These worlds should be dry, scorched, geologically dead. But atmospheric observations reveal water vapor, significant amounts, more than can be explained by cometary impacts or outgassing from ancient reservoirs. So, where is it coming from? Researchers built laboratory simulations of planetary interiors under extreme pressure and temperature. They compressed mineral samples to pressures equivalent to deep planetary mantles and heated them to thousands of degrees, and they watched the minerals break apart. At extreme conditions, certain silicate minerals decompose. The crystal structure collapses, oxygen atoms are released, and when those oxygen atoms encounter hydrogen, which exists abundantly in planetary cores, they combine. They produce water. Not just trace amounts. The lab experiments suggest that under the right conditions, a planet's mantle could generate water equal to 1/3 of its total mass. 1/3. That's more water than all of Earth's oceans combined, locked inside the deep interior of a world we thought was lifeless. This changes everything. Planets we classified as inhabitable might be oceanic underneath. Worlds that look dead on the surface might have vast subsurface hydrospheres, separated from space by hundreds of kilometers of solid rock. It overturns our assumptions about habitability, about planetary evolution, about where life might exist in the galaxy. And it means we need to rethink what a habitable world actually looks like. While scientists digest these discoveries, a new telescope in Chile has started operations, and it's showing us things we've never seen before. This isn't a typical observatory. The mirror is 8 meters across, massive by any standard, but the unique feature is the optical system, a giant wide-field design that can capture large sections of the sky in a single exposure. For the first time, we can see large-scale structures without stitching together dozens of individual images. We can observe entire galaxies, their surroundings, their halos, all at once. And immediately, the telescope found something unexpected. A crime scene in starlight. The first major discovery came from an observation of the galaxy M61, a large spiral galaxy, similar in size to the Milky Way, located about 50 million light-years away. The telescope captured the galaxy and its surroundings in a single frame, and in that image, faint against the darkness, there was a stellar stream, a long, thin arc of stars trailing away from the galaxy's edge. This is the signature of galactic cannibalism. At some point in the recent past, astronomically speaking, M61 consumed a smaller satellite galaxy. The gravitational interaction ripped the smaller galaxy apart, scattering its stars into long tidal streams that now orbit the larger galaxy like ghosts.
The evidence was always there, but previous observations couldn't capture the full structure in one view. You'd see fragments, disconnected pieces, and have to infer the rest. Now, with this new telescope, the entire crime scene is visible. A frozen moment of violence written in starlight. But that's not all the telescope found. During a single exposure of a different region, the telescope detected something else. Streaks, hundreds of them, colored streaks moving across the frame. Asteroids. The telescope uses multi-filter imaging, capturing the same field in different wavelengths. Objects that move between exposures leave colored trails, blue on one end, red on the other, depending on which filter was active when. The software automatically flagged the streaks and counted them. 2,100 previously unknown asteroids in a single image. 2,100 objects that had never been catalogued before, just sitting there in our solar system, waiting to be noticed.
And this was just one field, one random section of sky. The solar system is far more crowded than we realized. We've been mapping the major players for decades, the big asteroids, the near-Earth objects, the potentially hazardous bodies. But the small stuff, the meter-sized rocks, the fragments, the debris field from billions of years of collisions, that's still mostly invisible until now. This telescope is going to catalogue millions of new objects over the next few years. It's going to show us what the solar system really looks like when you turn on the lights. And some of those objects, statistically speaking, will have the wrong velocity, the wrong trajectory, the wrong isotopes. Some of them will be interstellar. Let's step back for a moment and look at the bigger picture, because something is happening, and it's not subtle. Interstellar objects are arriving. Atlas, with its inverted chemistry and radiation-hardened crust. Oumuamua, with its unexplained acceleration. Interstellar meteors hitting Earth's atmosphere at impossible velocities. Fragments recovered from the ocean floor with chemical signatures that don't match our solar system. We're detecting more of these objects now because our instruments are better, our sky surveys are deeper, our satellites are more sensitive. But the objects themselves have always been here. They've been passing through for millions of years. We just weren't looking carefully enough. And now that we are, the numbers are unsettling. The simulations suggest there could be tens of thousands of interstellar objects in the inner solar system at any given time. Most are small, invisible, undetectable. But they're there. A constant flow of material from other star systems drifting through the galaxy, occasionally intersecting our orbit. Some are icy, some are rocky, some are metallic. Each one carries the chemical fingerprint of a different stellar environment, a different formation history, a different cosmic neighborhood. And Earth sits in the middle of this invisible swarm, getting hit constantly by debris we can't see and don't understand. That raises an obvious question. What else is out there? Here's what we know for certain. The solar system is not isolated. It never was. We've been treating it as a closed system for so long, studying our planets, our comets, our asteroids, as if they represent the only data set that matters. But that's not true. We're part of a galaxy, and the galaxy is in motion. Stars drift past each other. Planetary systems interact gravitationally. Material gets exchanged. Objects get ejected. And some of those objects end up here. For the first time in human history, we're not just observing the galaxy from a distance. The galaxy is brushing against us, directly, physically. We're collecting samples from other star systems just by waiting for them to arrive. This is the dawn of a new field, interstellar astronomy, not with telescopes pointing outward, but with instruments pointing at our own backyard, analyzing the debris that drifts in from beyond. And the implications are staggering. Every interstellar object carries information about its home system, about the chemistry of its stellar neighborhood, about the planets it might have formed near, about the processes that ejected it into the void, about the radiation environment it traveled through for billions of years. Each one is a message in a bottle thrown into the galactic ocean, waiting for someone to find it and read what's inside. We're starting to read those messages now. Atlas told us about planetary systems with inverted volatile ratios. The Pacific meteor told us about metallurgy in foreign stellar environments. The Russian fireball might tell us about formation processes we've never considered. And there are more coming, always more. The simulations suggest we should detect 1 or 2 large interstellar objects every year with current survey capabilities. As our instruments improve, that number will increase. We'll start cataloguing dozens, then hundreds. We'll build databases of interstellar chemistry. We'll map the distribution of material types based on galactic coordinates. We'll start to see patterns. And eventually, we'll find something that doesn't fit the pattern. Something that can't be explained by natural processes. Something with the wrong spectrum, the wrong structure, the wrong behavior. Something that makes scientists uncomfortable. We're not there yet. Everything we've detected so far can be explained as natural objects with unusual properties. Atlas is a comet, just a weird one. Oumuamua was probably a nitrogen iceberg, even if that's a stretch. The interstellar meteors are rocks from other star systems, strange but explicable. But the sample size is growing. And with each new detection, the statistical likelihood of finding something truly anomalous increases. What happens when we detect an object that's clearly artificial? What happens when the spectroscopic data shows manufactured alloys? What happens when the trajectory is too precise, too controlled, too purposeful? It's not a science fiction question anymore. It's a statistical inevitability. If technological civilizations exist elsewhere, and if they've been around for millions or billions of years, then statistically, some of their artifacts should be drifting through interstellar space. Derelict probes, discarded stages, debris from long-dead missions. And sooner or later, one of them will pass through our solar system. The question isn't if, the question is when, and whether we'll recognize it when it arrives. Right now, astronomers are monitoring Atlas as it moves away from the Sun. They're measuring its brightness, tracking any changes in activity, analyzing the composition of the gases still escaping from its nucleus. The comet is fading. That's expected. As it moves farther from solar heating, the sublimation slows down, the coma disperses. Eventually, it will become too dim to observe, and it will disappear back into the darkness.
But before that happens, scientists are hoping to see if the radiation crust erodes enough to reveal pristine material underneath. If the solar heating stripped away that 5-meter shell, we might get a glimpse of the original ice from the comet's birth system. That's the opportunity. A chance to analyze unmodified material from another star. To see what a planetary system looked like before radiation and time transformed it. The telescopes are watching. The spectrometers are running. The data is streaming in. And somewhere near Jupiter, a spacecraft is flying through the dark, instruments active, hoping to intercept a tail of gas from an object that has traveled farther and longer than anything humanity has ever built. If the crossing happens, we'll know within days. The data will download. The mass spectrometer readings will show particles with isotope ratios that don't match anything in our solar system. And for the first time, we'll have physical proof, not just spectroscopic inference, of where this visitor came from. That's the next step. Physical samples, direct analysis, chemistry you can hold in your hand, even if it's just a few atoms captured on a detector. And after that, after we've analyzed our 3rd interstellar visitor and started cataloguing the 4th and 5th and 10th, after we've built a database of interstellar chemistry and mapped the flow of debris through the galaxy, after we've re-examined every meteorite in every collection and identified the ones that came from beyond. What happens when the statistics shift?
when we detect something that's one standard deviation too strange, 2 standard deviations, 3. That's what some researchers are quietly thinking about now. Not publicly, not in press releases, but in private conversations, in late-night emails, in the margins of conference presentations. What do we do when we find something we can't explain? There's a concept in signal processing called the detection threshold. It's the level at which a signal becomes strong enough to distinguish from background noise. Below the threshold, you can't be sure if what you're seeing is real or just random fluctuation. Above the threshold, the signal is undeniable. Right now, interstellar objects are just barely above the detection threshold. We're confident they exist. We've catalogued them 3 times, we've recovered fragments from at least 1 meteor. The data is solid, but the interpretation is still fuzzy. We're looking at strange chemistry, unusual trajectories, anomalous behavior, and we're explaining it all with natural processes stretched to their limits. Oumuamua's acceleration, outgassing from a nitrogen iceberg. Atlas's inverted composition, formation in the outer regions of a cold planetary system. The Pacific meteor's strange alloys, unfamiliar metallurgy from a different stellar environment. All of these explanations are plausible. Barely. They require specific conditions, unlikely scenarios, edge cases in the models. But they work technically. The question is, how many edge cases can you stack before the explanation becomes more implausible than the alternative? That's the threshold astronomers are watching for. Not a single smoking gun, but an accumulation of anomalies that, taken together, suggest something we haven't considered. And we're getting close. Not because any one object is definitively artificial, but because the pattern is becoming visible. The frequency of interstellar detections is increasing. The chemistry is getting stranger. The behaviors are harder to model. And every time we improve our instruments, we find more objects that don't quite fit. This is how paradigm shifts happen. Not with a single revolutionary discovery, but with a slow accumulation of data that doesn't match the existing framework. Until one day, someone publishes a paper that reinterprets everything, and suddenly the anomalies make sense. We're not there yet, but the trajectory is clear. There's an unspoken understanding in the astronomical community right now. You can hear it in the careful language of research papers, in the way scientists phrase their conclusions, in the questions they ask during conference presentations. Nobody wants to be the first to say it, but everyone is thinking it. What if some of these objects aren't natural? Not Atlas specifically, not Oumuamua necessarily, but statistically, over time, with millions of objects drifting through the galaxy, some of them have to be artificial. That's not speculation, that's just probability. And if that's true, then the question becomes, how do we recognize them? What does an artificial interstellar object look like after 1 billion years of travel? Does it still function? Does it still have recognizable technology? Or has it been so degraded by radiation, by micrometeorite impacts, by time itself, that it's indistinguishable from a natural rock? These are questions without answers, because we've never seen one. We have no reference point, no comparison, no database of this is what alien spacecraft debris looks like. So we do the only thing we can do. We observe, we measure, we catalogue, and we wait for something to be so obviously anomalous that it forces us to reconsider everything. That moment might be years away, it might be decades, or it might be happening right now, and we just don't realize it yet. Here's the final thought. For billions of years, the solar system existed in relative isolation. Objects formed here, stayed here, evolved here. Our planets, our comets, our asteroids, all products of the same primordial nebula that collapsed to form the Sun. But that isolation was never complete. It was just invisible to us. The galaxy was always there, streaming past, depositing debris, exchanging material. We just didn't have the instruments to see it. Now we do. And what we're seeing is that the door between our solar system and the rest of the galaxy has always been open. Material flows through constantly. Some of it is ice, some of it is rock, some of it is metal, and some of it, statistically inevitably, has to be something else.
We're at the beginning of this story, the first chapter, the part where astronomers are still figuring out what questions to ask. But the objects are arriving, the data is accumulating, the catalogues are growing. And somewhere out there, drifting through the darkness, is an object that will force us to rewrite everything we thought we understood about our place in the galaxy. It might be the next interstellar comet. It might be a meteor that hits tomorrow. It might be something we've already catalogued, sitting in a database, waiting for someone to notice the anomaly in the numbers. But it's coming. That's the statistical certainty. The galaxy is vast. Civilizations, if they exist, have had billions of years to spread their presence across interstellar space. And we've just started looking. The real question isn't whether we'll find evidence of something beyond natural objects. The real question is whether we're ready for what that evidence will mean. Right now, tonight, objects are crossing the boundary of our solar system. Some are ice, some are rock, some have been traveling for billions of years, and we're watching them arrive, one by one, learning to read the messages they carry. Space has stopped being quiet, and we're only beginning to understand what that means.